last few lectures we have been talking about social network properties mainly, and the immediate previous lecture we talked a little bit about social roles and the idea of equivalences, and we also introduced the specific case of structural equivalence, where we said that two nodes are structurally equivalent if they are perfectly substitutable in the network, that is they have the exactly same set of neighbors, as we saw in the last example if you look at the slides. Okay. So, we had this same Wassermann-Faust graph, and then we said that nodes E, F and H and I are structurally equivalent to one another, and that is why you see they define a equivalence class in themselves. Now, the point is that in many cases it is very difficult to find, in many real graphs it is very difficult to find exact structurally equivalent pairs of nodes. So, what we basically resort to is some sort of degree or extent of structural equivalence. So, basically the idea is that if although we do not have many cases where two nodes are perfectly substitutable, but are there cases which are like almost substitutable. The question is like, are there cases which are almost substitutable. So, in order to do this, in order to have a quantitative understanding for this, what we have to basically look into, as we saw for structural equivalence, we have to look into say the neighborhood, and the proxy for structural equivalence will be the count of number of common neighbors. Between a pair of nodes. So, basically let us take a small example and see. Say for instance, you have two nodes here, one named x and the other named y. Now, say also they have a bunch of neighbors a, b, c, d, G and H. Now, suppose the neighborhood structure is defined like this by the black edges that I am drawing. So, you see, if you look at this example, what you find is that node x and node y has a common neighborhood of 4 other nodes a, b, c, d, whereas x has 2 other neighbors g and h which are not connected to y, and y similarly has 2 other neighbors f and e which are not connected in any way to x. So, basically we quantify the extent of equivalence or the extent of structural equivalence in terms of the number of common neighbors between every pair of nodes in the graph. So, now how to estimate this? So, if you look at the adjacency matrix, so imagine the adjacency matrix of a graph. So, if I call that adjacency matrix A, every entry, the ijth entry, so this is the adjacency matrix, now the ijth entry, which we sometimes refer to as Aij, is basically denotes if node I and j are neighbors in the network. So, in this way, so if you look at the adjacency matrix, you can find out all the neighbors of I. Okay. So, what will this be? So, the row corresponding to I will give you all the neighbors of I. So basically I will have a row in the adjacency matrix of size 1 to n minus 1 if there are n nodes in the graph, okay, actually 0 to n minus 1 including I. So if there are n nodes in the graph, and then you have 0, 1, 2 and so on and so forth. So if node I is a neighbor of node 0, then you put a 1. If it is not a neighbor of node 0, then you put a 0. In this way you make a vector of neighbors of vector representing the neighborhood of I. Similarly, you can construct a vector representing the neighborhood of j. Now given these two vectors, you can very easily find out the common neighborhood. What will be this? Now the common neighborhood, basically if you look into these two vectors, the points where both of the entries in these two vectors are 1 indicate that both of them have this particular node common as their neighbor. Okay. So if you just simply take the product of the two vectors, you get a notion of the common neighborhood basically. So that is what. So we call Nij the number of common neighbors, and this can be calculated as using the following formula: Aik Akj for all such case where both Aik is 1 and Akj is 1, this value will be 1, otherwise it will be 0. If any one of them is 0 and the other is 1, or both of them are 0, this value will be 0. Only when both of them are 1, that is both I is a neighbor of k and j is a neighbor of k. In all such cases, this factor, this product will lead up to 1, and this will give you the count of the common neighbors between I and j, between the pair I and j. So if you note carefully, this also expresses, Nij also expresses the ijth entry of the A square matrix. So that is the adjacency matrix squared, okay, the adjacency matrix made a product with itself. Okay. So that the A square matrix, every entry in the A square matrix is nothing but Nij, that is the number of common neighbors between I and j. Okay. So in this way also Nij can be interpreted. Now see, we are telling that we want to quantify the extent or the degree of structural equivalence, and number of common neighbors is the proxy that we want to use. But then, like if you have if there is a pair which out of 100 neighbors, 100 total neighbors have a common neighborhood of 3, and there is another one which out of 10 common neighbors have a total neighborhood of 3, that makes a difference actually. So basically what I am trying to point out is that this particular factor needs to be appropriately normalized. So Nij needs to be appropriately normalized to correctly express the degree of equivalence. Fine. So in order to do this appropriate normalization, we resort to various different methods. The first method that we will talk about is, please look at the slides, the first method that we will talk about is cosine similarity. So what does this cosine similarity say? So cosine similarity basically tries to measure the cosine angle between a pair of vectors. Okay, the cosine similarity tries to measure the cosine angle between a pair of vectors. So here, as we said in the last part, that you can express every node in the graph as a vector of its neighborhood. Okay. Now if you take the cosine similarity between these two vectors, say the vector for representing the neighborhood of I and the vector representing the neighborhood of j. Now if you take the cosine similarity or the cosine angle between these two vectors, then if this cosine angle is 0, that means the the angle is 0 means that they are perfectly aligned. These two vectors are perfectly aligned, that is they are exactly the same. Okay. So, that means cos theta in this case will be 1, right. Whereas, if these two are completely orthogonal to each other, then the theta angle will be 90 degree and cos theta will be 0. So, basically perfectly similar cases will have a cosine angle of 1, we will have a cosine angle of 0 with cos theta evaluating to 1, and perfectly orthogonal cases will have a cosine angle of 90 degree with cos theta evaluating to 90. Now, this actually is expressed by the formula that you see on the slide. So, take two nodes x and y and say x is the vector corresponding to node I and y is the vector corresponding to the node j. So, x represents the neighborhood vector for node I and y represents the neighborhood vector for node j. So, cos theta is calculated as x dot y by the normalization, by the norm of x multiplied by the norm of y. Okay. So, this is in terms of the entries of the adjacency matrix. This is, so this cos theta, if the theta angle is 0, then cos theta will evaluate to 1 and that is perfect alignment. Okay. That is, the two nodes are completely structurally equivalent, whereas if theta is 90 degree, then cos theta evaluates to 0 and they are not at all equivalent. Okay. So, now this in terms of the entries of the adjacency matrix will result into the formula that I write in the last pointer of the slide, sigma ij. So, sigma ij is basically sum over k aik kj, which is nothing but nij, as we have seen last time. Okay. So, this is the number of common neighbors between I and j, between the nodes I and j. This is also measured by this dot product here. Okay. So, whereas the normalization is goes like this, it is the square root of the sum of all k, sum over all k a I k square into square root of sum over all k a k j square. So, this is nothing but the square root of the product of the degrees of these two different matrices, assuming that the adjacency matrix is a 0 1 matrix. If the adjacency matrix is a 0 1 matrix, then sum of the square of its elements will be nothing but the degree of that node. Okay. Similarly, for I you have a degree, for j you have a degree, and the normalization factor is nothing but the square root of the product of the degrees. Okay. So, now finally, you have sigma ij, that is the cosine similarity, is equal to nij, which is the number of common neighbors, by square root of ki kj, where ki is the degree of node I, kj is the degree of node j, and nij is the number of common neighbors between I and j, okay, between nodes I and j. So, this is the estimate of structural equivalence in terms of cosine similarity. This is the estimate of structural equivalence or similarity in terms of cosine similarity. So, similarly, you can also design various other metrics. Okay. So, the next metric that we will look into is the Pearson correlation coefficient. So, basically again, as we saw earlier, that node I and node j can be represented by neighborhood vectors like these. Okay. So, now given the neighborhood vector of I and j, you can basically find out. So, these are basically can be assumed as the terms or the variables. Okay. And so there will be one vector containing all the neighbors of containing neighborhood information of I or all the neighbors of I, whereas there is another vector which contains all the neighbors of j. Now you can find out, so these are you can treat these two set of numbers as a distribution in themselves. Now you can find out basically the Pearson correlation coefficient between these two numbers. So what I mean to say, suppose you have two nodes I and j, and you have, so with node number 0 I is connected, j is not connected. With node number 1 I is not connected, j is connected, and so on and so forth. Then maybe to node number 2 both of them are connected, to node number 3 both of them are connected, and so on and so forth. Okay. So now given these two columns, you can easily find out the Pearson correlation between the two columns, okay, two sets of items, okay, and that is actually measured using this particular formula that you see on this slide. So it is basically the covariance of xi xj by square root of variance of xi into variance of xj. So the square root of xi, covariance of xi xj can be calculated as the product of aik and ajk. So that is nothing but nij, as we have already defined, minus, as I already said, that for correlation analysis you usually take out the term which is possible just by random chance. So by random chance, if two nodes having a particular degree becomes neighbors, okay, so we take out that factor, we discount that factor. So this is basically the covariance by the square root of ki minus ki square by n into square root of kj minus kj square by n, that is the square root of the variances of each of the distributions, okay, the distribution of neighborhood of I and the distribution of neighborhood of j. So in this way you can compute the Pearson correlation coefficient between these two vectors. Now if the Pearson correlation is high, that means if it is close to, very close to 1, then this is an indication that the two nodes are structurally highly equivalent, whereas if this is low or negative, okay, then this would mean that the two nodes are not structurally very equivalent to each other, okay. So this is another way of defining the degree of structural equivalence. There is yet another method where we use the Euclidean distance, okay. So again, since these are binary vectors, node, the neighborhood can be represented as a binary vector like this, and the neighborhood of j can also be represented as a binary vector like this, also here the same thing. So then you can find out basically the Euclidean distance between this particular vector here and this particular vector here. So since this is a 0 1 vector, both of them, Euclidean distance also is proportional to the Hamming distance basically. So you can basically find out the Hamming distance between these two binary vectors, but again Hamming distance or the Euclidean distance. So they should be proportional in this particular case because it is a binary vector. So once you have calculated this, you have to also appropriately normalize. So what could be a nice normalization technique here? So you remember in the first case we normalized for the cosine similarity, we normalized by square root of ki kj. In the second case we normalized again by the square root of the variance of xi and the variance of xj, square root of the product of the variance of xi and the variance of xj, okay. Similarly we need to find out a normalization factor here. So if you look carefully, so the worst possible case is that none of the neighbors of I, okay, are similar to the neighbors of j. So then in such a case, what is the extreme Euclidean distance? Okay, the extreme Euclidean distance in this case is that the neighborhood overlap is 0. That means the Euclidean distance would be the sum of the degrees of the two nodes. Basically if you take node I, say its degree is ki, and you take node j, say its degree is kj. Now none of these nodes here are overlapping with these nodes here. So that means the distance in this case is basically ki with plus kj, because none of them overlap. So there is no overlap between them. So the straightforward, the total distance between these two nodes, neighborhood distance between these two nodes, the overlap distance between these two nodes is ki plus kj. So you can use this particular term as the normalization factor, Okay. So, you find out what is the overlap by the worst possible case. Okay. So, this is how you can find out. So, this is the maximum distance that is possible, okay, and you find out what is the exact distance. Now, here the lower the distance, the better. Okay. You know the exact distance, if this distance is low, normalized by this particular maximal distance, okay, then you say that these two nodes are structurally very similar to each other, otherwise they are very different. Okay. So, in this way we quantify one of the very first types of social roles, that is the structural equivalence. So, the next thing that we will get introduced to is called the automorphic equivalence. So, in order to understand automorphic equivalence, we have to first identify and understand the concept of isomorphism of graphs. Now, this is a very simple concept. So, we will slowly define it using a set of examples. So, an isomorphism is defined as follows. So, this is a mapping So, an isomorphism is a mapping. So, mapping means a function, okay, is a mapping P from one graph to another graph where if a node U is tied or connected to a node V in the first graph, then the node P of U should be connected to PV in the second graph. So, basically an isomorphism is a form of mapping. We say we define this mapping as P from one graph to another graph, such that if there is a edge between two nodes U and V in the first graph, then there will be an edge in the between the nodes PU and PV in the second graph, okay, and this mapping is a bijection. Okay. So, this mapping is a bijective mapping. So, we will take an example, a typical example of isomorphism, and then establish the concept of automorphism. Let us take these two graphs. So, let us call this graph G1 and this graph G2. Now, we can actually construct a mapping P between these two graphs as follows. G1, G2. So, the node number A in the graph G1 can map to node number Q, okay, in G2. Similarly, B in G1 will map to Z. Similarly, C in G1 will map to Y, D will map to P, and E will map to X. So, in this way you can actually establish a nice mapping relationship, a bijective mapping between the two graphs G1 and G2, and therefore, G1 and G2 are called isomorphic to one another. So, using this concept we can now describe automorphism. So, automorphism is nothing but an isomorphism from one graph to the same graph itself. Okay. Automorphism can be defined as an isomorphism of one graph to the same graph itself. Fine. So, this is what is called automorphism. Again, let us take an example and see. So, let us take this graph here. So, we can again define mappings on the graph. Say let us call this graph G. We can have various forms of automorphic mappings here, at least two that we can immediately find out. PG is our first kind, P prime G another kind of automorphism. So, in one case, so basically automorphism actually, so remember automorphism actually constitutes the notion of symmetry. Notion of symmetry in a graph. So, basically here again you see this symmetry is very apparent. So, look at the line of symmetry indicated by these broken red lines. Okay. So, now you can see that if you take this as the line of symmetry, then A is automorphic to B, D is automorphic to C, F is automorphic to E, similarly B is automorphic to A, C is automorphic to D, and E is automorphic to F. On the other hand, you can also construct another line of symmetry across the horizontal plane. Okay. Here the automorphism or the isomorphism is established between A can map to F, D maps to D itself, F will map to A, B will map to E, C will map to C itself, and E will map to F. So, in this way you can construct a automorphism for a given graph. So, automorphism, as I am telling you again, I am reiterating the fact that automorphism actually constitutes the symmetric structure, okay, present in a graph. So, it actually captures the symmetry associated with a particular graph. So, we will stop here.